Noche cósmica.
Imagine standing beneath a clear night sky, the kind of darkness where the Milky Way spreads itself across the heavens in a vast, milky brushstroke, thousands upon thousands of stars arranging themselves in patterns that have guided travelers and dreamers for millennia. The air around you is still, silent perhaps, except for the distant sound of wind moving through trees, or the occasional call of a night bird settling into sleep. You feel the cool darkness envelope you, and there is a profound sense of isolation, of standing alone beneath the infinite. But here is what you are not aware of, what cannot be seen or heard or felt in any ordinary way, and yet is happening at this very moment, has been happening every moment of every night and every day since the earth was young. Above your head, passing through the atmosphere in a gentle, ceaseless rain, are countless particles from deep space. These particles are traveling at nearly the speed of light. They have journeyed across unimaginable distances through the darkness between stars, sometimes for millions of years, and they are arriving at this planet, at this atmosphere, at this very place where you stand, in a continuous, invisible cascade that never pauses, never rests, never announces itself. These are cosmic rays, and they are falling through you right now. If you find yourself drawn into the quiet mysteries of how the universe actually works, the physics that hums beneath our notice, the gentle forces that shape our world in ways we rarely stop to consider, I would like to invite you to subscribe to this channel. We explore the most relaxing facts about cosmic rays and the deeper physics of space, taking time to unfold these stories slowly, letting their strange beauty settle into your mind as you drift towards sleep. Each journey through the universe's quieter truths begins with curiosity and ends in calm. So please, if you would like to return here for more slow voyages through the cosmos, I hope you will subscribe. Now, let us turn our full attention to what is happening in the darkness above. For a long time, for nearly all of human history in fact, cosmic rays were entirely invisible to us, not because they were rare or faint, but simply because we had no instruments sensitive enough to detect them. The night sky that ancient peoples gazed upon was the night sky of the stars themselves, the fixed points of light that seemed to wheel overhead in eternal, unchanging patterns. The cosmic rain was there, but unnoticed, unacknowledged, part of the universe's secret life. And yet the Earth's atmosphere and magnetic field were already working to protect you, to shield you from much of this invisible bombardment, creating a kind of vast, invisible umbrella that you live beneath every moment of your existence, and you would never know any different. But what makes cosmic rays so strangely soothing to contemplate, once you understand them, is that they are not violent intruders into our world. They are not weapons or dangers or sources of alarm. They are, in a very real sense, part of the fabric of what keeps our planet in a state of gentle balance. They come from the cosmos like a whisper, like the faintest breath of the universe's ancient history, telling us stories about explosions that happened long before the Earth existed, about the death of massive stars, about the slow, patient acceleration of particles across the emptiness of space. They pass through the atmosphere almost unimpeded. They pass through the buildings where we sleep. They pass through our bodies themselves, through every atom of our flesh, and most of the time, they cause no harm whatsoever. They are simply traveling through, continuing their ancient journey, indifferent to us, asking nothing of us, yet somehow connecting us to the greater cosmos in a way that is both humbling and deeply, profoundly peaceful. The very word cosmic carries a weight with it, does it not? It suggests vastness, antiquity, the incomprehensible scale of the universe itself. And yet when we look at cosmic rays themselves, these solitary protons, these stripped atomic nuclei, these lone particles wandering through the darkness, There is something almost tender about them. They are fragments. They are the scattered remnants of something larger, something that once burned or exploded or collapsed into itself. They have been broken apart, ionized, sent spinning into the void, and they drift for eons until, perhaps, they encounter our world, our atmosphere, our sky. What could be more patient than this? What could speak more quietly of the patient, relentless passage of time? To stand beneath the stars and know that this rain is falling, to understand that we live in the gentle shelter of layers of protection, the magnetosphere above, the atmosphere around us, that intercept and slow and scatter and deflect these particles from the depths of space, is to feel, in a very quiet way, held, not imprisoned or trapped, but held, the way a child might be held in the arms of something ancient and vast and entirely indifferent to its own vastness. The cosmos does not cradle us in the way that a mother might cradle a child, with intention and love, but it does surround us, does protect us through nothing more than the simple physics of how matter and energy behave across unimaginable distances and timescales. And so, as you lie here in the darkness, as your own breathing slows and your eyes grow heavy, and as the day's concerns begin to fade like distant stars disappearing beneath the horizon, know that you are resting beneath that vast shield, that ancient protection, while above it all, the cosmic rays continue their slow, eternal journey through the darkness, falling like snow through an infinite night, silent and persistent and utterly without end. Picture yourself in the early morning darkness of August 1912, somewhere over the Austrian Alps. The earth below is still sleeping. Victor Hess, a 33-year-old physicist with a curious mind and a willingness to chase mysteries into the sky, is ascending in a hot air balloon. He carries with him an electroscope, a delicate instrument designed to detect electrical charge, to sense the presence of invisible radiation in the air around him. It is not a journey he has made on a whim. For years, physicists on the ground had been puzzling over a persistent mystery. Their electroscopes, even when carefully shielded from obvious sources of radioactivity, continued to register faint electrical discharges. Where was this radiation coming from? The leading theory of the time suggested that natural radioactivity in the Earth's crust, uranium, thorium, and radium buried deep in the soil, was somehow sending their influence upward through the atmosphere, gradually ionizing the air and creating this mysterious charge. It seemed reasonable. Radioactive decay was known. The Earth contained radioactive elements. The mathematics pointed downward, toward the ground beneath our feet. And yet something about the observation nagged at Hess. He wondered what would happen if he rose high enough, far enough from that radioactive Earth. Would the mysterious radiation fade away? Or would it persist? So he climbed. The balloon rose steadily into the Austrian dawn. His instruments hung in their cases, silent companions to his curiosity. As the altitude increased, Hess carefully recorded his measurements, his hand steady despite the cold and the swaying of the basket. 2,000 meters, 3,000 meters, higher and higher, the Earth receding below, becoming smaller and more distant. If the radiation truly came from the ground, it should grow fainter. The distance alone should diminish it. Simple geometry, simple physics. But the electroscope told a different story. Rather than weakening as he climbed away from the Earth's surface, the readings grew stronger. By the time Hess had reached 4,000 meters, a height where the air was thin and the ground was a patchwork of distant fields, the ionization had nearly doubled. He continued upward, driven now by the quiet intensity of discovery. What he was witnessing contradicted the accepted wisdom. The radiation was not coming from below, it was coming from somewhere else, from above, from the cosmos itself. The significance of this moment, floating alone in that balloon in the cool morning air, can be difficult to grasp from our vantage point more than a century later. Hess was touching the edge of something vast and previously unknown. He was gathering the first human evidence that the sky itself was alive with particles and energy, raining down from the stars in an invisible deluge. Later, other researchers would confirm his findings and refine them. They would conduct their own balloon flights, their own careful measurements. But Hess was the first to ask the right question, and more importantly, to trust what his instruments told him when the answer proved surprising. There is something deeply moving about the image of a single scientist in a balloon, rising through the darkness with nothing but curiosity and instruments, discovering something fundamental about our place in the universe. He was not in a grand laboratory surrounded by colleagues. He was alone, suspended between Earth and space, in a moment of profound solitude and equally profound connection. The universe had been sending these particles all along, traveling across vast distances, passing through the atmosphere, passing through the bodies of every living thing, but no one had thought to look upward. No one had thought to climb high enough to feel their presence directly. What Hess had discovered, what he had proven through careful measurement and the courage to let his data speak against conventional wisdom, was the first tangible evidence of something that would come to dominate 20th century physics. The recognition that we live in a cosmos far more active, far more violent in its distant corners, far more filled with motion and energy than the night sky's peaceful appearance might suggest. Yet there was something strangely calming about this discovery too. These particles were not new. They had been falling through the atmosphere since the beginning of time. Life on Earth had evolved in their presence. They had moved through the bodies of dinosaurs and ancient humans and countless generations of plants and animals. We had always been breathing them in, walking through them, being touched by them in the most intimate way. Hess's balloon flight simply made visible what had always been true. The slow journey upward into the dark, the gradual realization that the instruments were registering something unexpected, the quiet moment of understanding that the universe was far stranger and more alive than anyone had imagined. This was how the first chapter of our cosmic ray story began, not with fanfare or announcement, but with one person willing to ask a question and float toward the answer, even when it led somewhere no one had expected to go. These cosmic rays that fall around us, through us, past us in the endless night, what are they really? The answer is both simple and ancient. They are, in their overwhelming majority, lonesome protons. Single protons, the bare nucleus of hydrogen, stripped of everything else, wandering through space as a solitary particle of light mass and singular purpose, though purpose perhaps is too deliberate a word for something so patient and untethered. But protons are only part of the story. Woven through this cosmic rain are atomic nuclei of heavier elements, helium nuclei, carbon nuclei, iron nuclei, all of them torn free from their parent atoms long ago, ionized by the violence, or the time, or the mysterious energies that set them on their journeys. Imagine an atom, complete and whole, and then imagine every electron stripped away, leaving behind only the dense charged core. That core, that skeleton of an atom, is what travels, and it travels alone. These particles have been wandering. That is the quietest fact about them, and perhaps the most profound. A cosmic ray proton that arrives at Earth's atmosphere this moment may have been traveling for millions of years, or longer, or far longer. We cannot always know their age with precision, but we know they are ancient travelers. They were accelerated, set in motion, in some distant event, a stellar explosion, a collision in the far reaches of the galaxy, processes we will touch upon more gently as we move deeper into this journey. And then they moved, through the galactic dark, through regions where stars are so few that the distance between them dwarfs any human measurement, through the cold that does not feel cold because there is almost nothing to feel it. They moved in silence, at tremendous speed, fractions of the speed of light, some of them, crossing the void. What does a proton look like? The honest answer is that it does not look like anything, because it is far too small to reflect light or be seen in any conventional sense. But if we were to imagine it, we might think of it as impossibly tiny, a diameter of perhaps 100 millionths of a nanometer, a quantity so small that billions upon billions could fit in the space of a grain of sand. Yet despite this diminutive scale, this proton carries energy. It carries momentum. It carries the memory, in a way, of the violence or the process that launched it, and it has held that energy across millions of years and trillions of miles. The nuclei of heavier elements, those carbon cores and iron cores, are similarly minuscule, yet similarly energetic. They are rare compared to the protons. For every heavier nucleus, there might be dozens of protons, but they arrive nonetheless, part of this vast and ancient diaspora of particles flowing from the depths of the galaxy toward us. What is remarkable, and what settles into the mind like a sedative truth, is that these particles are not new. They are not products of today or yesterday. They are not generated freshly by some nearby source and sent immediately to Earth. They are refugees from events billions of years old, travelers from the far side of the galaxy, particles that have outlasted empires and species, that have crossed emptiness that would make the human mind ache if we truly grasped it. And now, in this quiet moment, they are here, arriving continuously, thousands upon thousands per square meter per second in the upper atmosphere, each one a visitor from a time before human language existed, from a place we may never directly see. They arrive stripped of their history, in a sense. We cannot look at a single proton and divine where it came from or when it began its journey. We only know, through careful statistical observation and the mathematics that physicists have developed over decades, that they come from far away, that they have been traveling for ages beyond our counting, and that they arrive with energies that speak to the profound violence of their acceleration somewhere in the cosmic past. To know that every particle passing through your body right now, and particles are passing through you constantly, even as you move towards sleep, to know that each one may be millions of years old, may have crossed the galaxy from a star system that has since evolved beyond recognition, may have been flung outward by an explosion that sent its light toward us eons ago. This knowledge brings a certain peace. It places us in a continuity. It makes us part of something vast and ancient and patient. These particles ask nothing of us. They do not harm us, for the most part, though we will explore what happens when they meet the upper atmosphere. They simply pass through, continuing their eternal journeys, indifferent to our small lives and our small moments of attention. They are among the most abundant massive particles in the universe, and yet we notice them only when we build sensitive instruments to listen for them, when we learn to read the whispers they leave behind. So as these cosmic ray protons and nuclei drift through the night sky above you, as they pass through the roof and walls of your shelter, as they move through the air you breathe, know that they are ancient travelers. They are pieces of the far cosmos brought near. They are a form of connection between this moment and moments billions of years past, between this place and the vast regions of space from which they come. They are, in their quiet way, one of the universe's most eloquent reminders that everything is connected across time and distance, and that stillness and patience are qualities we share, in some form, with the cosmos itself. These ancient nuclei, these wanderers born in the violent moments of dying stars, do not rush toward us. They move through the vacuum of space with patient determination, and if you were to imagine their journey not as something terrifying, but as something almost meditative, the perspective shifts entirely. A cosmic ray proton that arrives at the top of Earth's atmosphere tonight might have been traveling through the interstellar medium for millions of years, perhaps 10 million, perhaps far longer than that. The light years they cross are not obstacles to overcome, but distances they simply inhabit, moving at nearly the speed of light, yet taking millennia to complete their journeys across the thickest parts of the galaxy. Consider what this means when you think of scale, not as something vast and overwhelming, but as something gentle and slow. A cosmic ray beginning its voyage from a supernova remnant in Orion, 3,500 light-years away, is embarking on what we might compare to a cosmic snowfall. Imagine snowflakes drifting down through the atmosphere, not on a winter evening, but across centuries and millennia, each one arriving with its own quiet purpose, its own path determined by the magnetic fields that guide it through the dark. The flakes do not hurry. They tumble through space with a constancy that feels almost restful when you consider it deeply. The vastness of these distances, measured in light years and passed in the language of astronomy, can feel abstract and cold unless you let yourself sit with what it actually means. A light year is the distance that light itself, the fastest thing we know, travels in 1 year through the vacuum. That is nearly 6 trillion miles. Now imagine a proton, far more modest than light, traveling that distance not once but many times over, threading its way through clouds of gas and around magnetic obstacles, sometimes deflected, sometimes accelerated again by fields it encounters, moving always at nearly light speed, but nonetheless taking its geological time to reach us. The journey is not frantic, it is patient, it is the opposite of urgency. What makes this contemplative rather than frightening is the constancy of it all. These cosmic rays do not arrive in waves of emergency. They drift in what we might call a cosmic steady state, a background rain so gentle and so ordinary that your own body barely notices it. The Earth has been receiving this rain for billions of years. Life has evolved in its presence. Forests have grown tall. Oceans have swallowed and surrendered continents. And through it all, these particles have continued their silent fall, aging particles from aging stars, tracing paths through the darkness that took longer to complete than human civilizations have existed. The comparison to snowfall deepens when you consider the actual density of these arrivals. Cosmic rays do not bombard us. They arrive instead in a quiet, sparse pattern. Individual particles separated by volumes of space that sound vast when spoken, but feel almost peaceful when imagined as the ordinary condition of the universe. A single cosmic ray might pass through your body once every few minutes, but not in a concentrated rush. The distribution is even, unhurried, the rhythm of it almost meditative if you surrender to the idea that this is simply how things are. The photographic plates that early 20th century physicists used to detect cosmic rays often waited weeks or months before recording a single clear track. That long patience required by observation mirrors the patience inherent in the cosmic rays themselves. They are not impatient particles. They are travelers that have learned the meaning of time on a scale so vast that 1,000,000 years passes like an afternoon, and yet they arrive. Through the mathematical precision of stellar physics and the patient unfolding of cause and effect across the cosmos, they arrive at precisely the moments and locations determined by laws we have only begun to understand. There is something soothing in surrendering to such scales. When you step back far enough, the journey of a cosmic ray from a dying star to the top of Earth's atmosphere becomes not a dramatic race, but a slow, inevitable waltz choreographed by gravity and magnetism and the physics of charged particles in vast fields. The proton does not strain, it simply moves, deflected here, accelerated there, pulled this way and that, by the invisible architecture of the universe, finding its way across light years with the inevitability of a river finding the sea. And when it arrives, when it finally penetrates the edge of our planet's protective shell after its millions of years of travel, It has become part of a pattern so old and so vast that your individual receiving of it is less like a sudden event and more like being brushed by something that has always been there, something eternal and gentle and utterly indifferent to the small anxieties of the creatures who live below. And yet the most generous gift of cosmic rays does not come from across the impossible gulfs between galaxies. It comes from much closer. It comes, in fact, from the slow funeral pyres burning quietly in our own corner of the Milky Way, from the remnants of stars that ended their lives in tremendous violence, and left behind a kind of gentle, perpetual humming that continues even now to shake loose the particles we receive. When a massive star reaches the end of its long life and collapses, it does not simply vanish. Instead, it detonates. The explosion we call a supernova is, in human terms, nearly unimaginable in its ferocity. A single star suddenly outshining an entire galaxy of billions. But what concerns us here is not the flash itself, which fades within months or years, but rather what happens in the centuries and millennia that follow. The expanding shell of gas and stellar debris does not drift away quietly into the vacuum. Instead, it becomes something far more interesting, an accelerator, a cosmic machine that takes the nuclei it has scattered and, through mechanisms we are still learning to understand, drives them to higher and higher speeds. Imagine, if you will, a vast bubble of superheated material expanding outward from the site where a star once burned. The shock wave at its edge is not smooth, but turbulent, filled with knots and regions of intense magnetic chaos. When a nucleus from that explosion finds itself caught at this edge, buffeted by the magnetic field lines that thread through the shock, it can be jostled and accelerated again and again, gaining energy with each encounter, much as a pinball bounces higher with each striking post. This process, which physicists call diffusive shock acceleration, can continue not for seconds or minutes, but for centuries. A single nucleus might spend 100 years or more trapped in this cosmic game, gaining energy incrementally until it reaches speeds approaching that of light itself. What emerges from this slow violence, then, is a stream of tremendously energetic particles, mostly protons, along with some heavier nuclei, that eventually escape the remnant and begin their journey outward through the galaxy. These are cosmic rays born locally, you might say, within perhaps 1,000 light-years of where we now sit. They are the offspring of stellar death, particles that have been carefully, patiently accelerated by the dying convulsions of a star. But the story does not end when the supernova remnant has finished its acceleration work. The remnant itself does not simply cool and fade. Instead, it enters a long quiescent phase that can extend for tens of thousands of years. During this time, the shell of gas continues to expand, growing thinner, becoming less dense. The shock wave weakens, the acceleration process slows, and yet the whole structure hums with a kind of quiet energy. Observations from radio telescopes and X-ray satellites reveal that these old remnants continue to emit radiation, a kind of slow afterglow that marks their continued interaction with the interstellar medium, the thin gas and dust that fills the space between stars. This aftermath phase is where something quite beautiful happens, in its own subtle way. The expanding shell encounters clouds of this interstellar material, and the collision generates new waves, new disturbances in the magnetic field. These do not accelerate particles to the extreme energies that the initial shock wave did, but they represent a gentler, prolonged process of energy transfer. The remnant becomes a kind of low-burning fire, warm at the edges where it meets the surrounding material, quietly maintaining its role as a source of energetic particles even as its most violent phase has long passed. Gradually, over millennia, the distinction between the remnant and its surroundings becomes less clear. The boundary of the expanding shell merges with the background. The structure that was once a distinct bubble begins to dissolve back into the general interstellar medium from which the original star was born. In some cases, multiple remnants from different eras overlap, creating regions of the galaxy where the ambient magnetic field is particularly rich with energy, particularly good at maintaining and preserving high-velocity particles. These ancient supernova remnants, some of them dating back tens of thousands of years, some even older, form a kind of distributed network of cosmic ray sources throughout our local region of the galaxy. A particle born from one explosion 10,000 years ago might still be wandering nearby, its energy slowly declining through collisions and radiation, but still capable of making the journey to Earth. In a very real sense, the cosmic rays we experience today carry within them the history of stellar violence in our corner of space. They are a kind of message, written in energy and momentum, from events that unfolded long before our world existed. What is perhaps most soothing to contemplate is the profound silence and stillness of this entire process. Yes, the physics involves tremendous energies and violent events, and yet from our vantage point, from the calm darkness of a quiet night, none of this is visible. No light, no sound, no sensation marks the passage of these accelerated particles through the spaces around us. The supernova remnants continue their slow expansion, their gradual dissipation, their patient work of acceleration and release, all while we move through our days entirely unaware of their distant industry. And yet, while these ancient wanderers drift through the darkness from distant stars, there exists closer to home a far more immediate and intimate source of cosmic activity. Our Sun, that great patient furnace at the center of our planetary system, maintains its own subtle conversation with the cosmos, and this dialogue occasionally sends its own charged messengers spiraling toward Earth in what we might think of as a kind of stellar exhalation. These solar energetic particles, as physicists call them, are born not from the violent death of a distant star, but from the Sun's own breathing, its rhythmic pulsing magnetic life. The Sun's magnetism is never still. Deep within its convecting core, electrical currents twist and coil in patterns we are only beginning to understand, and this creates a magnetic field of tremendous complexity and power. This field extends far beyond the Sun's visible surface, spreading outward through space in vast, invisible loops and spirals, threading through the entire inner solar system in a structure sometimes called the solar wind's magnetic architecture. Every 11 years or so, the Sun's magnetic personality shifts dramatically. The field grows tangled and turbulent, and then it reorganizes itself, flipping its poles in a gentle cosmic act of renewal. During these periods of magnetic shifting, particularly around the maximum phase of this cycle, the Sun becomes more prone to sudden eruptions. Coronal mass ejections hurl billions of tons of plasma into space, and solar flares release sudden bursts of electromagnetic radiation and energetic particles in brilliant, violent cascades. It is from these moments of solar temper that solar energetic particles are born. These particles move far faster than the cosmic rays arriving from distant galaxies, where galactic cosmic rays may have wandered the space between stars for millions of years, gathering speed through the ages. Solar energetic particles reach Earth in mere minutes. Picture, if you will, the moment after a solar flare erupts. The Sun's magnetic field snaps and reconfigures, and in that instant, protons and heavier nuclei are accelerated to tremendous speeds, flung outward like sparks from a struck flint. They stream across the 93 million miles separating the Sun from Earth in waves of pure energy, arriving with such force and velocity that their kinetic power rivals that of meteorite impacts. Yet they come often unseen, their presence detected only by instruments we have placed in orbit or by the subtle ways they interact with our planetary atmosphere. The Sun's 11-year rhythm itself has a meditative quality to it, a vast cycle of activity and quiescence that has been ticking in the background of Earth's history for billions of years. During quiet phases, the Sun is kinder. Its magnetic field is more orderly, its eruptions fewer, and the stream of solar energetic particles dwindles to a gentle trickle. But during active phases, during solar maximum, the Sun seems almost irritable, its surface boiling with sunspots, those dark regions where magnetic field lines bunch and tangle. From these sunspots, flares erupt with regularity. Have you ever considered that the solar activity you might read about in news reports of geomagnetic storms is simply part of a rhythm as old as the Sun itself? These cycles have been happening for longer than anything resembling human consciousness has existed on this planet. The passage of solar energetic particles through the solar system is not random or chaotic. They tend to flow along the Sun's extended magnetic field lines, traveling outward in preferred directions, carried by the solar wind as a river carries leaves upon its surface. When the Sun's magnetic field is oriented such that these pathways lead toward Earth, our planet receives an increased flux of solar particles. This is why space weather forecasters can predict, sometimes days in advance, that a solar energetic particle event is heading our way. The particles themselves carry information about the Sun's magnetic topology, creating what researchers might describe as a kind of solar magnetic shadow or imprint, evidence of the field's current configuration frozen into the particles' trajectories. What makes this particularly soothing to contemplate is how orderly it all remains, despite the apparent chaos of solar eruptions. The Sun's cycles are dependable. Scientists maintain detailed records spanning centuries, and in those records lies a kind of narrative quiet. We know the Sun will erupt. We know it will calm again. We know this rhythm will continue, largely unchanged, for billions of years to come. Even the most violent solar flares, dramatic as they seem, are merely the Sun releasing energy that it was always going to release, following patterns as natural and inevitable as the turning of the seasons. And yet, despite this endless cascade of ancient particles drifting through the void toward our small, sleeping world, the surface beneath your rest remains untouched by the vast majority of them. There is a reason for this profound quietness, this shelter we inhabit without consciously knowing it exists. The Earth, it turns out, has wrapped itself in two extraordinary layers of protection, each one working in concert with the other in a rhythm as old as the planet itself, a lullaby of magnetic and atmospheric shielding that has been sung into being by forces we are only beginning to fully understand. The first of these guardians, and perhaps the more powerful, is the magnetosphere, an invisible bubble of magnetic energy that extends far outward into space, born from the churning iron core deep beneath the crust, that great dynamo of molten metal turning slowly in the planet's belly. This magnetic field reaches outward for tens of thousands of kilometers, creating a vast asymmetrical halo around the Earth, wider on the night side where the solar wind pushes it gently outward, compressed on the day side into a tighter shape like a comet's tail pointing away from the Sun. It is within this space that most of the cosmic ray particles are gently diverted, their charged electrical nature meaning they follow the curved paths of magnetic field lines rather than plunging straight through. Think of it as an enormous, invisible fortress, not built of stone, but of pure geometry, of invisible forces that guide and redirect without ever touching. When a cosmic ray proton, having traveled for millions of years through the patient dark, finally encounters Earth's magnetic shield, it does not crash through in a violent collision. Instead, it curves along invisible pathways, following the contours of the field, like water flowing around a smooth stone. Many are turned back entirely, sent spiraling away into the depths of space from which they came. Others penetrate deeper, drawn inexorably toward the polar regions where the field lines compress and funnel more steeply into the atmosphere. This is not a harsh, sudden barrier. It is more akin to a gentle redirection, a cosmic traffic system that channels the incoming stream away from the populated middle latitudes, where most of humanity rests its head in sleep. And then there is the second protective embrace, the atmosphere itself, that thin, precious shell of air and gas that wraps around the entire planet like a quilt. We think of it often as a collection of gases to breathe, a medium for wind and weather, but it is also a profound shield against cosmic radiation. The particles that do penetrate the magnetosphere's initial defense encounter the upper reaches of the atmosphere, and there they meet their most intimate ordeal. The air molecules, nitrogen, oxygen, the trace elements suspended in this invisible ocean above us, begin to absorb the energy of the incoming cosmic rays. Collisions occur, not violent collisions that generate light or heat you could detect, but subtle interactions that transform the cosmic particle into a cascade of secondary particles, each one gentler than the last, each collision releasing a little more of the original particle's tremendous energy into the surrounding atmosphere, dispersing it as harmless heat. By the time you are breathing at sea level, by the time your skin and your eyes and your lungs are exposed to the open sky, the cosmic ray bombardment has been reduced to a fraction of its intensity at the top of the atmosphere. The thickest part of the air blanket, the lowest several kilometers, absorbs perhaps 95% of the radiation that would otherwise reach you. It is a slow, patient filtering process that has been occurring every single moment since the atmosphere first formed billions of years ago. The cosmic rays that do reach the surface have been transformed, gentled, reduced to a manageable trickle of particles that your body encounters with such regularity that your cells have evolved mechanisms to handle them, to repair the occasional damage they might cause. What is most remarkable about this two-layered system is that it functions without thought, without intention, without any conscious effort on the planet's part. The magnetosphere does not decide to protect you. The atmosphere does not choose to filter the cosmic rays. These are simply the way the world works, the way physical laws arrange themselves when you have a spinning iron core and a blanket of gases suspended by gravity. They are the reason you can sleep peacefully without the fear of invisible particles piercing through the roof and into your chest. They are the reason the surface of the Earth, despite being located within a cosmic shower of radiation, remains one of the safest places in the solar system for life to flourish and rest. And as you lie there in the darkness, the starlight filtering through the windows comes from sources that may themselves have generated some of the very cosmic rays that are at this moment encountering your planet's shields. You are surrounded, always, by this quiet architecture of protection. The magnetic field hums its inaudible song around you, the atmosphere continues its patient work of gentle filtering, and the surface stays calm, undisturbed, a safe harbor in the midst of a universe in constant motion. When those torrents of charged particles meet the magnetosphere's protective shell at the polar regions, something quite extraordinary occurs, not violent or sudden, but gradual and painterly, as if the cosmos were slowly drawing with colored light across the highest reaches of night. This is where the invisible becomes momentarily, breathtakingly visible. The aurora borealis, the northern lights, is perhaps the most beautiful consequence of that ancient cosmic rain falling through our atmosphere, and it unfolds with a slowness that rewards patient observation. Picture the scene at high latitudes on a clear evening, when solar activity stirs. The sun, millions of miles away, has released a surge of its own energetic particles, a solar wind gust carrying electrons and protons, and these have traveled outward, eventually colliding with Earth's magnetic field. The magnetosphere, that great invisible cocoon, becomes briefly animated by this influx. The charged particles are guided, funneled, spiraled by the planet's magnetic geometry toward the polar caps, where the field lines converge like the threads of a great cosmic net, drawing everything inward. As these particles descend into the upper atmosphere, that thin, dark realm perhaps 80 to 300 kilometers above the Earth's surface, they begin to collide with the sparse molecules lingering there, oxygen and nitrogen mostly. These collisions are not harsh or chaotic, they are like gentle taps, each one transferring energy to an atmospheric atom, exciting its electrons to higher orbits. When those electrons release that energy, they emit light, visible light, colored light, and what unfolds is a slow dance across the polar sky. The colors themselves arise from the types of atoms involved and the altitudes where the collisions occur. Oxygen in the upper reaches tends to produce those deep, haunting emeralds and lime greens that characterize the classic northern lights, colors that seem to glow from within the sky itself rather than illuminate it from outside. Lower down, where the air grows denser, oxygen emits a deeper red, a crimson curtain that is sometimes visible above or between the greens. Nitrogen contributes purples and blues, especially at the edges where the display is most active, creating layers of color stacked like translucent silk scarves draped across the heavens. What makes the aurora so profoundly soothing to watch is its pace. This is not a lightning flash or a meteor streaking in seconds. An aurora unfolds over hours, sometimes the entire night. The curtains ripple and sway with the motion of the upper atmosphere and the shifting of particle streams, but the motion is slow, hypnotic, almost gentle. Observers describe them as drapes billowing in a wind only they can see, or as vast curtains being slowly drawn across the darkness. The light builds gradually, then fades. It intensifies in one region, dims in another. It breathes. There is something profoundly calming about recognizing that what you are witnessing is, in fact, the direct interaction of cosmic particles with the Earth's magnetic and atmospheric boundaries. You are watching, in real time, the visible trace of that cosmic rain. The sun's particles, carried on the solar wind, meeting the Earth's magnetic cage, spiraling downward, colliding with oxygen and nitrogen molecules, and transforming into photons that travel the last few kilometers to your eye. It is a conversation between the cosmos and our planet, written in light. Consider this. The aurora is, in a deep sense, a kind of cosmic feedback. The very shielding that protects us, that magnetosphere we spoke of earlier, is being illuminated by its own work. The particles are following the magnetic field lines, and as they do, they create this visible reminder of the protection that surrounds us constantly, invisibly. On most nights we sense nothing, but on these rare, clear evenings at high latitudes, the magnetosphere and atmosphere become briefly, tenderly luminous. The aurora australis, its southern hemisphere counterpart, exhibits these same qualities, these same slow cascades of color, though far fewer humans are positioned to observe it. The physics is identical, but there is something fitting about reserving this spectacle most prominently for the Arctic regions, where the long winter nights create the optimal conditions for watching. Darkness extending for hours, clear skies, and the patience required to see something that will not hurry. It rewards the watcher who sits still and allows time to pass in its own rhythm. When you consider the chain of events that produces an aurora, each step is almost absurdly gentle. The sun breathes out its particles. The magnetosphere guides them. The upper atmosphere accepts the collision. The electrons leap to new orbits and fall back, releasing their light. No explosions, no sudden transformations. Just an intricate, slow-moving sequence that has been happening, night after night, for billions of years. Long before humans existed to witness them, auroras were painting the polar nights in emerald and crimson. painting the sky for audiences of migrating birds and aurora-watching animals whose eyes, perhaps, saw beauty in what their minds could not name. There is a meditation in watching the aurora, a quieting that comes from understanding that you are observing the very boundary between Earth and space, made visible. The colorful echo you are seeing is the proof of that eternal rain of cosmic particles arriving, being caught, slowed, absorbed by the layers of protection that hold us all. It is as though the universe is gently reminding us that we are not separate from the cosmos, but embraced by it, held within fields and forces that we can see, at least for these few hours, written in slow light across the dark. When a cosmic ray enters the uppermost reaches of the atmosphere, it does not arrive alone. What happens next is a kind of quiet cascade, a gentle unfolding of creation that occurs every single moment, continuously, above and around us. The primary cosmic ray, that ancient proton or nucleus that has journeyed across light years, strikes the nucleus of an oxygen or nitrogen atom in the thin upper air. The collision releases tremendous energy in an instant, but this energy does not vanish. Instead, it transforms into something else entirely. A spray of secondary particles is born. These secondary particles tumble downward through the layers of air. Some are pions, short-lived messengers that decay almost immediately into muons and neutrinos. Others are lighter fragments of the shattered nucleus. And so begins the shower, the cascade, the gentle rain of particles that descends from the upper troposphere toward the ground, branching and multiplying as it falls. Each particle that is created can collide with another atom and create more particles still. The shower spreads outward and downward in a cone of activity, unraveling through the sky in a fraction of a second. Yet in the stillness of that fraction, countless new particles are born. What is remarkable, and what invites contemplation, is that this is happening right now. As you read these words, as you settle into the quiet hours of the night, cosmic ray showers are passing through the building around you. They are passing through the walls, they are passing through the air, and they are passing through your body. A single cosmic ray shower can produce hundreds, sometimes thousands of secondary particles. Most of these are muons. Muons are heavier cousins of electrons, particles that are unstable by nature and exist only for a fleeting moment before they transform into electrons and ghostly neutrinos. But in those brief instants they fall. They descend through the atmosphere at speeds approaching the speed of light itself, creating a thin cone of particle rain that strikes the ground and passes through everything in its path. The human body is largely transparent to muons. They slip through your skin, through your muscles, through your organs, leaving almost no trace. In a single night's rest, your body is penetrated by thousands of these particles. They pass through without damage, without sensation, without leaving any mark at all. This is perhaps the most soothing aspect of the cosmic ray shower. It is entirely harmless at sea level. The atmosphere has already absorbed the most dangerous particles. What reaches us are the gentle remnants, the secondary messengers that slip through like whispers. Consider the geometry of this moment. A shower that begins kilometers above your head spreads outward as it falls. If you were to stand next to someone just a few meters away, you might both be struck by the same cosmic ray shower, by the same spray of secondary particles descending from the same collision point in the upper air. The shower is wide enough to touch many people simultaneously, yet delicate enough to leave no impression, no sensation, no awareness of its passage. Early physicists discovered these showers through patient observation. They built cloud chambers, simple devices filled with vapor that would condense around the paths of charged particles, revealing their invisible trails. In the darkness of their laboratories, in the stillness of careful scientific work, they watched as tracks appeared and disappeared in the mist. These were the signatures of the shower, the visible evidence of particles that had no other way to announce their presence. The tracks branched and multiplied, painting a picture of the cascade that occurs every moment in the natural world. The shower is democratic in nature. It does not discriminate between the living and the non-living. A cosmic ray shower passes through a sleeping child with the same indifference as it passes through a tree, through the earth, through stone. It has been falling on this planet for billions of years, long before humans existed to study it. It will continue long after we are gone. There is something calming in this constancy, in the knowledge that this process unfolds without our participation or awareness, as reliable as the slow turning of the planet itself. What makes the shower particularly elegant, from a scientific perspective, is its structure. The particles are not distributed randomly. They form a pattern, a cone of activity that is densest near the center and thins toward the edges. The muons, being more penetrating than the lighter particles, travel the farthest. The electrons and photons are stopped more easily by the air molecules above. By the time the shower reaches the ground, it consists primarily of muons and ghostly neutrinos, particles so subtle that they barely interact with ordinary matter at all. The cascade continues downward, minute by minute, hour by hour, throughout the endless night. In urban areas, scientists have placed sensitive detectors on rooftops to count these showers. The rate is remarkably constant. Roughly one cosmic ray shower reaches the ground every few seconds across an area the size of a room. This means that while you sleep, dozens of showers pass through your home, hundreds pass through your city, thousands cross an entire continent. The numbers are so large they lose meaning, yet the reality they describe is perfectly ordinary. It is simply the texture of our universe, the constant gentle percussion of high-energy particles encountering the air above us. There is an invitation in understanding this phenomenon. Once you know that these showers are falling, you might imagine them during those quiet hours before dawn, that restful time when consciousness begins to dissolve. The showers are falling. They were falling an hour ago. They will fall an hour from now. The universe is conducting this experiment continuously, without fatigue, without doubt, without any need for observation or acknowledgement. The shower simply falls, particle by particle, through the darkness, through the sleep of the world, a gentle reminder that the cosmos is not distant. It is here, it is now, it is inside and around and everywhere, a quiet rain that never stops. In the early decades of the 20th century, physicists found themselves in possession of a puzzle that could not be solved by simply looking at the sky. The cosmic rays were there, striking the upper atmosphere with invisible persistence. But what happened to them in those first moments of collision remained hidden. To see what they could not observe directly, scientists turned to a device of almost meditative simplicity, the cloud chamber. Picture a glass box, sealed and perfectly still, containing air saturated with water vapor or alcohol mist. When a charged particle passes through this quiet space, it leaves behind a trail of condensed droplets, a gossamer thread of evidence marking its path like frost forming on a winter window. The chamber became a window into the hidden world. One of the most patient observers was Carl David Anderson, a young physicist working at the California Institute of Technology in the early 1930s. Anderson would sit in darkened laboratories with photographic plates positioned beside these chambers, waiting for the rare and precious moments when a cosmic ray collision would leave its mark. Night after night, the work continued with a rhythm that was almost meditative. The particles arriving from space would occasionally strike the chamber, and in that instant of collision, secondary particles would be born. Anderson, with meticulous care, would photograph these trails, study them, measure them, and record their behaviors. Each plate was like a page in a slow opening book, each image a word in a story that the cosmos was whispering into the chamber. What began to emerge from these images was something unexpected. Anderson noticed trails that behaved like neither electrons nor protons. They had the electrical charge of an electron, negative and precise, but they were somehow heavier, moving with a different slowness through the magnetic field he applied to curve their paths. The deflection was gentler than an electron's would be, speaking of greater mass. He scrutinized the images with the focus of someone reading a letter written in cipher. Could these be something entirely new? A particle that had never been seen before, that had never been predicted in theory? The discovery took time, as all true discoveries do. It was not a flash of sudden understanding, but rather a gradual accumulation of certainty, measurement after measurement, confirming what the cloud chamber trails were telling him. By 1936, Anderson had gathered enough evidence to declare his discovery to the scientific world. He had found the muon, a particle with the mass of roughly 200 electrons, yet carrying a single negative charge like its much lighter cousin. The muon, it would later be understood, was born constantly in the upper atmosphere when cosmic ray protons collided with nitrogen and oxygen nuclei. Thousands of them rain through our bodies every single moment, passing through us with such swift indifference that they cause us no harm. They are like invisible visitors that pause only long enough to say they were here, and then they are gone, decaying into lighter particles and ghostly neutrinos. But the cloud chamber had yet more secrets to reveal. As scientists continued their patient observations, other trails appeared that did not match any known particle either. These paths sometimes curved in one direction, sometimes in another. Sometimes they seemed to carry positive charge, sometimes negative. Sometimes they moved with the weight of something heavier still. The puzzle pieces multiplied. These were the pions, particles even more short-lived than the muons, decaying almost instantaneously into muons and neutrinos. The pions were the primary products of cosmic ray collisions, the first generation of secondary particles born from the impact of a galactic proton striking an atmospheric nucleus. They lived for only fractions of a microsecond before transforming into something else. There was something almost poignant about discovering particles that existed for such vanishingly brief intervals. The pions and muons were not there long enough to be observed directly in any static way. They could only be known through their signatures, through the traces they left behind as they raced through the apparatus. In a sense, physicists were reconstructing the story of cosmic events from fragments, the way an archaeologist might reconstruct an ancient civilization from scattered shards of pottery. The cloud chamber became not merely a detector, but an instrument of historical reconstruction, allowing the present-day observer to witness the consequences of collisions that happened instantaneously, microseconds in the past, thousands of kilometers above the Earth. The elegance of these discoveries lay in their simplicity. No grand accelerator was needed, no enormous expenditure of energy to create these particles. They were created constantly, for free, by the cosmic rays themselves, delivered as a gift from the galaxy to anyone patient enough to look. The universe was conducting an experiment continuously, and the physicists had merely learned to read the results. Each cloud chamber image was a message from space, a tiny confirmation that the cosmic bombardment was not just a theoretical concept or a mathematical abstraction, but a real, physical phenomenon happening in the present moment. What strikes the mind as one contemplates these discoveries is the slowness with which the truth emerged. There were no sudden revelations, no dramatic moments of insight. Instead, there was careful work, night after night, image after image, measurement after measurement. The physicists trusted their instruments and their observations. They allowed the data to speak, and they listened with patience and precision. In doing so, they unveiled not just new particles, but a deeper understanding of the cosmic rain itself. The cloud chambers had transformed invisible cosmic rays into visible stories, written in water droplets and traced by particles that existed for only the briefest instant. And in those brief instants, the story of the cosmos was being continuously written, a narrative of creation and transformation that plays out silently in the upper atmosphere above us, moment after moment, day and night, without pause or hurry. Now, in the quietest corners of evolutionary biology, there exists a thought that shifts our perspective on life itself, a possibility that reaches backward through time, suggesting that the very cosmic rain we've been following might have gently nudged the direction of all living things. It's a contemplation that sits at the intersection of the infinitely small and the profoundly vast, and like many beautiful scientific ideas, it lives in a space of thoughtful uncertainty rather than hard proof. Consider for a moment what a cosmic ray does when it strikes living tissue. Deep within the nucleus of a cell, where DNA coils in its silent, elegant way, one of these ancient particles can leave a mark, a mutation. Most mutations, we know, are harmless or quietly destructive. But a few, scattered across the vast canvas of billions of organisms across billions of years, sometimes alter the instructions in ways that change what an organism becomes. A creature slightly faster, another with new resistance, a third with a subtle alteration in form that, by chance, finds a use in a changing world. The question that evolutionary biologists have gently posed is this: did cosmic rays, in their relentless bombardment through our atmosphere and down through our bodies, contribute to the supply of random variation that natural selection works upon? It's a difficult thing to measure, yet it rests on something we know to be true. Cosmic rays do cause mutations. The evidence is clear and calm. We see this in laboratory settings where radiation exposure increases mutation rates. We observe it in the records of living things. The connection feels plausible, even elegant. What makes this idea so peacefully intriguing is that it removes a layer of separation between the stars and life itself. You might say that cosmic rays, born in the violent deaths of distant stars, traveled silently across the galaxy only to arrive at Earth, where they entered the quiet conversation between chance and selection that has shaped every organism alive today. A supernova exploded millions of years ago. Its scattered debris cooled and drifted. Some of that radiation eventually found its way through the magnetosphere, down through the air, and into the ancestor of something that would one day evolve into a different form because of that single, random encounter. But, and it's important to rest with this but for a moment, we must hold this idea lightly. Science is at its best when it remains honest about what it knows and what it merely suspects. The precise contribution of cosmic rays to the mutation rate on Earth's surface, historically and today, remains difficult to calculate with certainty. The atmosphere provides shielding. The magnetosphere provides more. The rate of cosmic ray strikes varies with latitude, with solar cycles, with the geological epochs. Some mutations come from other sources entirely: the natural decay of radioactive elements within the Earth, ultraviolet light, chemical damage. Disentangling cosmic rays' particular influence is like trying to isolate a single thread from a tapestry woven in darkness. There have been attempts, of course. Scientists have looked at evolutionary rates during times when Earth's magnetic field was weaker, when more cosmic radiation might have reached the surface. They've examined the fossil record for accelerations or changes in the pace of speciation. These studies whisper suggestively rather than shout conclusions. Some researchers have wondered whether cosmic rays might have played a role in triggering rapid evolutionary changes, or whether they've contributed a steady background hum of genetic novelty over deep time. Others remain more cautious, noting that the mathematical models are complex and the historical record fragmented. What we can say, without hesitation, is that life on Earth has always existed within this cosmic shower. Every cell that has ever lived has been touched, countless times, by particles from space. The organisms that survived and thrived and gave rise to all the complexity we see today, all of them experienced this radiation. It was part of their environment, as constant as gravity, as present as the air. In that sense, cosmic rays weren't an interruption to evolution, but a condition of it, a quiet accompaniment to the unfolding of life. There's something restful in contemplating this possibility, isn't there? The idea that the universe has not been separate from life, watching from a distance, but has been gently involved in its own quiet way. Mutations that might otherwise seem purely random gain a different kind of poetry when you know they might have been seeded by the debris of ancient stars. It doesn't answer the ultimate questions about how life began or where it's heading, but it does suggest that the boundary between the cosmic and the biological is more permeable than it sometimes appears. And so we move forward through this knowledge, understanding that cosmic rays may have written themselves into the very code of life, page by patient page, throughout the long, quiet history of Earth. Not with certainty, but with the kind of thoughtful respect that science gives to ideas that seem true, feel true, and rest at the edge of what we can measure and verify. The particles continue their journey, falling through the night sky as they always have, touching living things, leaving their marks, participating in a dance so slow that we can barely see it, even as we study it across the centuries. Yet there exists a deeper mystery still, one that settles quietly in the minds of those who study the very highest energies that the cosmos hurls toward us. For while most cosmic rays arrive as gentle whispers of radiation, carrying the slow, accumulated weight of ancient journeys across light years, there are rare arrivals of extraordinary intensity. Particles so energetic, so impossibly forceful, that a single cosmic ray can strike the upper atmosphere with the concentrated impact of a baseball thrown by a human hand. Imagine that, a single subatomic particle, so small it exists beyond any direct sight, compressed into it the kinetic force of something you could hold in your palm and hurl across a room. The energy is real, the arrival is real, yet where it comes from remains, even now, a gentle puzzle wrapped in scientific uncertainty. These ultra-high-energy cosmic rays are exceedingly rare, perhaps arriving once every 100 years over an area the size of a city. When they do strike, they create a cascade of secondary particles that spread out through the atmosphere like ripples of light. Observatories around the world have begun to map these events, catching their faint signatures in the nighttime sky, recording the whispered traces of their arrival. And yet, despite decades of careful observation, the astrophysicists who hunt these particles approach the question of their origin with a quiet, almost meditative humility. They do not claim certainty where none exists. Instead, they sit with the mystery, turning it over gently in their minds. The prevailing hypotheses are several, and each carries its own appeal, its own sense of possibility. Some believe these highest energy particles originate from the violent cores of active galaxies, from the regions surrounding supermassive black holes where jets of matter are expelled at relativistic speeds, where the ordinary rules of energy seem almost quaint by comparison. Others propose that the sources lie in the catastrophic deaths of massive stars, in the final moments when a hypernova releases more energy than our sun will produce in its entire lifetime. And still others wonder whether certain cosmic rays might originate from phenomena we have not yet recognized, from processes at the very edges of our understanding, perhaps from magnetic reconnection events in distant magnetospheres, perhaps from scenarios that have not yet entered the scientific imagination. What is striking, what offers a certain calm comfort in the face of such unknowing, is how the scientific community sits with this ignorance. There is no rush to fill the void with certainty. Instead, there is a steady, patient accumulation of data. Detectors grow more sensitive. Observations span longer periods. New telescopes come online, each one adding another piece to a puzzle that may take generations to complete. This is not a crisis of knowledge, but rather a natural frontier, a boundary between what we understand and what we have yet to discover. And it is a boundary that shifts slowly, almost imperceptibly, as evidence gathers in the quiet darkness of observatories and laboratories. The physics of these encounters raises its own gentle questions. When an ultra-high-energy cosmic ray strikes an atom in the upper atmosphere, the collision produces a shower of secondary particles that spreads outward in a cone shape. This cascade might contain billions of particles, each one carrying a fraction of the original energy. Some will reach the ground, others will dissipate high in the atmosphere, their energy transforming into light and heat and motion. The detectors that scientists have positioned across the planet's surface are arranged to catch these showers, to triangulate their origins and estimate their energies. But the act of observation reveals only aftermath, only the faint trace of the particle's arrival. The particle itself is long gone, its energy already spent in that first violent collision. There is something almost paradoxical in this situation, a kind of cosmic whisper. These are the most energetic particles we know of anywhere in the universe. They represent the extreme edge of the universe's capacity for acceleration. And yet they arrive so rarely that a human being could live an entire lifetime without ever being struck by one. They are simultaneously the most powerful and the most elusive. They are the universe's way, perhaps, of reminding us that scale and rarity are not the same as presence or importance. The question of their origin leads physicists to consider the structure of the cosmos itself. If these particles do indeed come from distant galaxies, from sources billions of light years away, then they must travel through a universe filled with radiation and magnetic fields, with obstacles both seen and unseen. Along the way, they interact with photons in the cosmic microwave background, losing energy gradually in a process called the GZK cutoff, named for the three physicists who predicted it decades before the particles were actually observed. This process means that ultra-high-energy cosmic rays from very distant sources would lose energy significantly during their journey, which suggests that the highest energy particles we observe today must originate within our own galactic neighborhood, within perhaps a few 100 million light-years. And yet, when astronomers look in the directions from which these particles seem to arrive, they often find nothing obviously special. No obvious supernova remnants, no obvious active galaxies, no obvious source at all. This tension between theory and observation, between what we expect and what we see, is where the real science happens. It is where curiosity lives. It is where future discoveries will emerge, slowly, patiently, like dawn breaking across a landscape you have never quite seen before. The scientists who work on this problem carry with them a particular kind of peace, the peace that comes from knowing that the universe is far larger and stranger than any single person's knowledge. They wait, they measure, they wonder, and in doing so, they continue that ancient human tradition of looking up into the darkness and asking, quietly, "What are you?" In the vast and quiet darkness of the Argentine pampas, where the land stretches flat and open beneath an enormous sky, there exists a peculiar kind of listening post. It is called the Pierre Auger Observatory, named after the physicist who first glimpsed cosmic ray showers in cloud chambers nearly a century ago, and it represents perhaps the most patient and contemplative way humanity has yet devised to hear the whispers of the cosmos. Imagine, if you will, thousands upon thousands of detectors spread across nearly 1,200 square kilometers of grassland, each one standing in stillness like a sentinel, waiting through the nights and days for the briefest signal of an ultra-high energy particle descending from the void. These are not grand monuments or gleaming instruments pointed skyward in aggressive questioning. Rather, they are humble things, simple tanks of purified water buried into the earth, or plastic scintillators arranged in a vast geometric pattern across the plains. From above, the landscape appears almost unchanged, as though the instruments have chosen to be invisible, to listen without announcing themselves. And indeed, there is something profoundly peaceful about this arrangement. The detectors do not search with urgency or strain, they simply stand and wait, because the rarest cosmic rays are so sparse, so infrequent in their arrival, that patience is the only strategy that works. Consider the mathematics of this quietude. A single detector might wait for months before capturing the unmistakable signature of an ultra-high energy cosmic ray. The entire observatory, spread across that immense expanse, might register only a handful per year, and yet the scientists who built it chose this deliberately. They understood that to study the rarest visitors from the cosmos required surrendering to a different rhythm of discovery, one measured in patient accumulation rather than immediate reward. There is a philosophical calm in this choice, is there not? A recognition that some mysteries demand we slow ourselves to their pace rather than imposing our own. When a cosmic ray of extraordinary energy does arrive, traveling at nearly the speed of light through the vacuum, it encounters the upper atmosphere and unleashes a cascade. In that fraction of a second, a vast shower of secondary particles blooms outward, spreading across the land below like a momentary flower opening in the dark. The detectors nearest to the point of impact register this cascade almost simultaneously. A sudden electrical pulse, a glimmer of light in the scintillator, a ripple of charged particles through the water tank. The instruments speak to each other across the plains, through fiber optic cables and radio signals. And from this network of quiet conversations, the scientists reconstruct the original cosmic ray's energy, its direction, its probable origin point in the distant sky. The wonder of the Pierre Auger Observatory lies not in its complexity, but in its elegance, and in the profound restraint of its design. There are no great domes housing telescopes, no whirring mechanisms or intense beams of light. Instead, there is the vast, patient openness of the Argentine landscape, and the simple presence of instruments waiting. The night sky above those plains hums with cosmic rays constantly, thousands striking the atmosphere every second, but only the most energetic, the most rare and violent, carry enough power to be registered by the spread of detectors. One might think of it as the observatory listening, not for all sounds, but only for those particular notes that truly matter. Picture the scientists who tend this place, driving across the pampas to maintain the detectors, replacing worn components, checking instruments that often work perfectly without any sign of distress or malfunction. There is something meditative in this work too, the routine of checking systems that function in profound silence, knowing that at any moment, though that moment might not come for weeks, something extraordinary might occur. This is not the dramatic science of sudden revelation, but the slow science of accumulation, of patterns emerging from patience and careful records. The altitude of the Argentine location was chosen with great deliberation, high enough to allow the cosmic ray showers to spread and be captured across multiple detectors, yet not so high as to be impractical for maintenance and care. The pampas themselves, relatively flat and unobstructed, provide an ideal surface for the spreading cascade to be read clearly by the array of instruments. And the clear, often cloudless skies mean that certain types of cosmic rays can be detected using the fluorescence technique as well, where the ultraviolet light produced by the cascade in the atmosphere is captured by telescopes trained on the sky above. So when you imagine the Pierre Auger Observatory, do not picture a place of frenetic activity or urgent searching. Picture instead a kind of cosmic temple of patience, a landscape consecrated to listening. Picture the flat horizon at dusk, the instruments standing in their countless positions like a thoughtful congregation. Picture the vast quietude interrupted only occasionally by the arrival of something extraordinary, something that fell from the depths of space-time itself. This is how we listen to the rarest visitors from the universe. Not with instruments that force answers, but with the gentle persistence of systems willing to wait for as long as it takes, through countless nights beneath the stars, for the cosmos to speak in its own time. When astronauts venture beyond the sphere of Earth's magnetosphere, they step out from beneath the most generous shelter our planet offers. The magnetic field that has cradled life for billions of years grows thinner, weaker, more diffuse the farther one drifts into the black. And in that thinning envelope, the rain of cosmic rays becomes something to be reckoned with, in a way that those of us bound to the surface need never truly contemplate. An astronaut orbiting within low Earth orbit, perhaps 300 or 400 kilometers above the surface, still enjoys the benefit of Earth's magnetic protection. The magnetosphere wraps around them still, its invisible arms reaching outward and around, deflecting the majority of incoming cosmic particles. But consider for a moment the astronaut who ventures to the moon, or beyond. The further they travel, the more directly exposed they become to the full, unfiltered stream of cosmic radiation, protons and alpha particles and heavier nuclei, all carrying their ancient energy across the void. The human body, that delicate arrangement of water and cells and electrical signals, receives radiation constantly here on the surface, yes, but in doses so small that our cells have evolved repair mechanisms to handle them. Our DNA knows how to stitch itself back together after the occasional cosmic ray tears through a strand. But in space, above the protective blanket of atmosphere and magnetism, the dose rises significantly. An astronaut on the moon receives something in the range of 200 to 300 times more cosmic radiation than someone standing on Earth. Picture that difference. Picture the cells receiving that much more energy, that many more impacts, that much greater demand upon the repair machinery within. Engineers and physicians have long wrestled with this quiet problem. How do you shield against radiation that arrives from every direction, that comes in particles of such tremendous energy that traditional shielding can sometimes make things worse? A thick lead wall might stop some cosmic rays, but in the process, it creates secondary radiation. It fragments the high-energy particles into showers of smaller, sometimes more dangerous particles. It is a puzzle without a simple answer, and the silence of this puzzle, the fact that it sits there waiting for the long human journeys yet to come, is rather profound. Some solutions propose the use of hydrogen-rich materials, plastics, water, even liquid hydrogen, because hydrogen atoms are light and plentiful, and they scatter incoming cosmic rays rather than absorbing them completely. A spacecraft surrounded by water, for instance, serves double duty. It provides drinking water and life support, while also gently pushing back against the cosmic wind. Other proposals suggest using the spacecraft's own structure strategically, positioning supplies and equipment as an outer shell, a quiet fortress of mundane things, arranged to protect the precious human beings within. There is also the slower, gentler shield of electromagnetic fields. Could a spacecraft generate its own miniature magnetosphere, its own artificial magnetic bubble, to deflect particles the way Earth's great shield deflects them? The idea hums with elegant possibility, though the energy required to maintain such a field and the technical challenges of implementation remain substantial. The future explorer drifting toward Mars might one day move within a cocoon of carefully managed magnetism, an invisible bulwark against the cosmic rain. And then there is the biological question, the one that sits quietly beneath all the engineering considerations. What does prolonged exposure to cosmic radiation do to the human mind, to cognition, to long-term memory and mood. Some research suggests that cosmic rays penetrating the brain might increase the risk of cognitive changes, though the evidence remains soft, debated, not yet settled. The astronaut in space is not merely protecting against cancer and genetic damage, they are protecting against the possibility of subtle shifts in how they think, how they process the extraordinary journey they are undertaking. There is something both humbling and sobering about that realization. The longer the voyage, the more pressing the problem becomes. A mission to Mars lasting 6 months or more would expose an astronaut to cumulative doses of radiation that carry real risks. The journey back adds further exposure. And then there is the question of Mars itself. It has virtually no magnetosphere, no substantial atmosphere to filter cosmic rays. An astronaut standing on the Martian surface would receive doses even higher than those in transit. Would they wear protective suits while outside, not merely against the thin, cold air, but against invisible particles? Would habitats be built underground, beneath Martian soil, that would serve as radiation's ancient enemy, mass and time and stone, providing the shelter that Mars's own planetary systems cannot? These are not the urgent crises that grab headlines. They are the slow, patient problems that engineers and scientists sit with, year after year, refining calculations, testing materials, running simulations in the quiet corners of laboratories. They are the kind of challenges that make space travel not a single leap, but a series of gentle progressions, each one solving a piece of the puzzle, each one bringing us incrementally closer to the day when human beings might walk on another world and remain there, safe within the layers of protection we have learnt to build. There is something almost peaceful about contemplating these solutions, these thoughtful human responses to the indifferent physics of the cosmos. We cannot change the cosmic rays. We cannot still the ancient supernovae that sent them spiraling toward us. But we can think and plan and create and solve. We can build shelters. We can dream of voyages protected not by the accidental magnetism of a spinning iron core, but by the intentional creativity of minds working toward the possibility of venturing farther than we have ever gone before. There exists a gentler mystery woven through all of this, one that takes us away from the high-altitude drama and the brilliant auroras, away from the cascade of secondary particles, and down instead into the quiet realm of water vapor and clouds. For decades now, scientists have wondered whether cosmic rays, in their patient passage through our atmosphere, might nudge the formation of clouds themselves, and through clouds, perhaps even influence the great rhythms of Earth's climate. It is a possibility that sits at the edge of certainty, shimmering like a mirage, neither quite confirmed nor dismissed. Picture, if you will, a cloud beginning to form. High in the atmosphere, where the air grows thin and cold, water vapor begins its subtle shift toward liquid. But there is a problem that atmospheric physicists have long understood. Water vapor alone cannot simply condense into droplets on its own. It needs a seed, a nucleus, some tiny solid particle around which the water can begin to gather. Dust from the desert, salt crystals from sea spray, sulfate particles from volcanic eruptions. These have always been there, these natural nuclei, floating quietly through the air. And yet, what if cosmic rays added their own influence to this ancient dance? The theory emerged most clearly in the work of a Danish physicist named Henrik Svensmark in the late 1990s. He proposed something deceptively simple. As cosmic rays stream through the lower atmosphere, they ionize molecules. They strip electrons away, creating ions. These ions, Svensmark suggested, might make it easier for water vapor to condense around them, to form those first microscopic droplets. If cosmic rays increase the ionization, the thinking went, then perhaps more clouds form. And if more clouds form, Earth grows cooler because clouds reflect sunlight back into space. Conversely, when cosmic ray flux decreases, fewer clouds might form and Earth warms. It is an elegant hypothesis, and one that immediately suggested a tantalizing connection. Could changes in solar activity, which modulates the flow of cosmic rays reaching Earth, be a hidden driver of our climate? When the sun's magnetic field strengthens, it shields Earth from more cosmic rays. When it weakens, more cosmic rays arrive. Thus, the solar cycle, through this mechanism, might influence cloud cover, which might influence global temperature. Over long timescales, over centuries and millennia, might this help explain some of Earth's natural climate variations? The idea captured imaginations. It offered a potential explanation for certain historical climate shifts. Yet, as the years have passed, the reality has proven far more complicated, far more nuanced than that initial spark of insight suggested. And in this very complication, in this scientific humility, lies something strangely soothing, the recognition that nature rarely permits simple answers. Multiple studies have tested Svensmark's hypothesis with increasing sophistication, using satellite data of cosmic ray intensity, cloud cover, and temperature trends. Some results have seemed to support the connection, others have found it weak or absent. The challenge lies partly in the nature of clouds themselves. They are profoundly complex, formed by 1,000 competing variables, influenced by atmospheric circulation patterns, by moisture content, by temperature gradients, by aerosol concentrations. Teasing out a single thread, cosmic rays, from this tapestry has proven surprisingly difficult. It is rather like listening for a single voice in a vast chorus. What current scientific consensus suggests, and here we move gently into the region of what we know most reliably, is that cosmic rays do indeed ionize atmospheric molecules. This part is unambiguous, well established, but the connection between this ionization and actual cloud formation remains subtle, modest, and difficult to isolate with certainty. Some laboratory experiments have shown that ions can promote the formation of nanoscale clusters, the very first aggregations of molecules that might grow into cloud droplets. Yet the leap from these laboratory findings to the vast, turbulent real atmosphere is considerable. Other atmospheric factors, wind shear, humidity patterns, the availability of conventional aerosol particles, appear to dominate the cloud formation process in most circumstances. This does not mean cosmic rays exert no influence at all. Rather, it suggests that influence is likely to be present but faint, woven subtly through the climate system, difficult to separate from the louder voices of atmospheric circulation and greenhouse gas concentrations. Think of it as a whisper beneath a conversation, present, perhaps even occasionally significant, but not the primary speaker. There is also the matter of timescale. The cosmic ray flux at Earth's surface does vary with solar activity cycles, yes, but these variations are gradual, typically spanning years or decades or longer. Meanwhile, clouds respond to weather patterns that shift daily, to seasonal rhythms that operate on much shorter timescales. The cosmic ray signal, if it exists as a climate driver, must be sought in longer records, in the slow accumulation of climate effects over centuries and millennia. This is painstaking work, requiring careful reconstruction of past cosmic ray intensities from proxy records, from ice cores that preserve radioactive isotopes, from tree rings that encode solar variability, and comparing these to climate reconstructions built from similar ancient archives. The picture that emerges is one of possibility rather than certainty, of correlation where causation remains to be proven. Yet here is where the story grows soothing again, in its own way. For the existence of this ongoing scientific debate, this careful weighing of evidence, this honest acknowledgement that we do not yet fully understand how cosmic rays might modulate clouds and climate, speaks to how much remains to be discovered about the Earth system. We live atop a planet of extraordinary sensitivity and subtlety, where even the faintest cosmic rain falling through the darkness might, through mechanisms we are still learning to perceive, touch the great cycles that govern whether regions flourish or wither. The cosmic rays continue their ancient descent. Their ionization persists, clouds form and dissolve in their daily dance, and the climate system evolves through patterns both understood and mysterious. Perhaps cosmic rays play a meaningful role in the centuries-long variations of Earth's climate. Perhaps their influence is negligible compared to the great drivers of atmospheric change. The answer, it seems, will require generations of further listening, further measurement, further patient thinking. And there is something deeply restful in that realization, that nature's secrets are not all solved, that there remains always more to learn, more wonder to encounter, in the interplay between the cosmos above and the living world below. And as we linger in this quiet understanding of cosmic rays arriving at our threshold, it becomes worth pausing to consider something that deepens the sense of timeless connection we have with the cosmos. The particles that pass through you tonight, the ones that shower down in cascades through your body and the night air, may have begun their journeys not as recent travelers from a nearby corner of the galaxy, but as messengers from catastrophes so ancient and so distant that their origins are woven into the very deep history of our stellar neighborhood. Think of it this way: the supernova remnants we spoke of earlier, those slowly expanding clouds of stellar debris still humming with activity across space. They existed not for decades or centuries, but across millennia, across the long, quiet epochs of human civilization. And the cosmic rays they accelerated and released in those distant explosions, some of them, have been drifting through the galaxy ever since, their energy gradually diminishing as they scatter through nebulae and stellar winds, yet still carrying within them the memory of that original cataclysm. Consider a particular ancient star. Let us imagine it lived for millions of years in some distant region of our Milky Way, burning steadily in the deep past, perhaps so far away that its light has only just now reached Earth, or arrived centuries ago, and we received it through our telescopes as a faint whisper of historical light. That star eventually exhausted its fuel and collapsed in upon itself. The core could not hold against its own weight, and in the final moments before the rebound, pressures and temperatures rose to impossible heights. And then, in a fraction of a second, the entire stellar architecture exploded outward. That explosion, that genuine cataclysm, did not merely scatter atoms into the void. It accelerated atomic nuclei to energies so vast that they were flung across light years, becoming cosmic rays that would wander the galaxy's dark lanes perhaps forever, or until they encountered an atmosphere, a planetary surface, a human being. The remarkable and strangely moving aspect of this is the temporal layering involved. At this very moment, as you rest and listen, photons from that ancient explosion may be arriving at Earth's surface, having traveled through the darkness of space for thousands or millions of years. Simultaneous with those photons are particles born in the same explosion, cosmic rays that have been drifting through the galaxy's magnetic fields, slowing, scattering, but persisting, and they too are arriving now. You could say, in a sense, that we are receiving the light and the echoes of ancient stellar deaths across different channels of perception. The light comes as visible memory, arriving through our eyes and our instruments. The cosmic rays come as invisible messengers, arriving through our atmosphere, through our magnetosphere's protective architecture, penetrating silently into our tissues. This raises something quietly profound about the distances and timescales involved. A cosmic ray, born in a supernova explosion in some distant arm of the galaxy, may have taken millions of years to reach us. During that entire journey, it was not moving at human scales or planetary scales, but rather drifting through the vast emptiness between stars. And yet, relatively speaking, it was traveling at nearly the speed of light. This seeming contradiction, a particle moving almost as fast as light is possible to move, and yet taking millions of years to complete its journey, speaks to the profound indifference of the universe to our ordinary sense of time. The particle experiences no time at all, frozen in relativistic suspension. To the particle, the journey is instantaneous. But to us, standing on Earth, the wait has been almost inconceivably long. That ancient star may have exploded while our planet was in the grip of an ice age, or during the reign of dinosaurs, or long before complex life had even begun to emerge in Earth's oceans. And only now, in this century, in this night, does its particle finally arrive at our world. What makes this even more subtle is that we cannot always know with certainty where a particular cosmic ray has come from. The magnetic fields of the galaxy, and indeed the magnetic fields woven throughout the interstellar medium, bend and redirect the paths of charged particles. A cosmic ray that strikes Earth tonight may have been redirected dozens of times since its creation, its trajectory altered by invisible magnetic currents across vast distances. So in a sense, tracing a cosmic ray back to its source is like trying to trace a river back to its origin by watching the current at any single point along its flow. The path curves, branches, loops back on itself in response to the terrain. Only through patient observation of many particles, through statistical analysis across enormous numbers of individual events, can we begin to infer something about the cosmic ray sources themselves, the populations of ancient explosions distributed throughout the galactic neighborhood. And there is a kind of strange continuity to this. Those supernova remnants that we discussed as active and recent events, the ones still accelerating particles in the present era through their expanding shockwaves, they are themselves the products of explosions that occurred centuries or millennia ago. Supernovae do not explode in bunches at any particular historical moment. Rather, they are scattered throughout time, and their remnants persist in various stages of decay and activity. Some are bright and vigorous, still young. Others are ancient and fading, their energy dissipating slowly into the surrounding medium. The cosmic rays they produced ages ago are meanwhile traveling outward from their sites of creation, some perhaps still carrying significant energy, others having surrendered most of their power through long interactions with the magnetic and particle fields of the galaxy. There is something genuinely soothing about contemplating this timeless rain of particles from dead stars. It is a form of connection that transcends the usual human scales of relationship and causation. You are not connected to another living person across a room or across a continent. Rather, you are connected through time and space to the catastrophic death of a star whose light may never even reach your eyes, whose explosion may have occurred during an era of Earth's history that left barely a trace in the fossil record. And yet one of its particles has found its way to you, has entered the atmosphere above your location on this spinning world, has descended through the clouds and layers of air, and perhaps through the roof of your dwelling, and has passed invisibly through your body. In some small way, then, we are all made of stardust that is literally still arriving, still being delivered to us across the eons by cosmic couriers that were launched when the universe was younger, when the stars that created them were still burning. This perspective, held gently in the mind as sleep approaches, can offer a form of solace. The cosmos is ancient and indifferent, yes, but it is not hostile, it is not chaotic. Rather, it operates according to laws that are steady and comprehensible, and within those laws, patterns emerge that have beauty and that offer connection. The cosmic rays are part of this pattern. They are part of the universe's breath, its slow exhalation of old matter and energy from the dying embers of its past, carrying forward the history of stellar lives and stellar deaths into the present moment where you rest and listen to their story. And so we arrive at the simplest and most complete picture of all. Somewhere above you right now, in the darkness between the stars, cosmic rays are falling. They have been falling for billions of years, will fall for billions more. They fall through the void of space with no sound, no hurry, no destination in mind. They simply drift and travel and arrive, moment after moment, in a ceaseless gentle rain that has never once paused since the universe learned to make them. Think of it this way, if you will. Across the electromagnetic canvas stretched overhead, across all the quiet physics that holds galaxies in their slow dance, there exists this one quiet constant, a murmur of particles, an ancient conversation between the explosive deaths of stars and the patient receiving of a world that has learned to live beneath their invisible descent. Every second of your life, thousands of these travelers pass through your body, through your dreams, through the darkness of sleep itself. They ask nothing of you. They do no harm. They are simply there, witnesses, messengers, echoes of the universe's oldest stories written in the language of physics. We have spent our entire journey following these wayfarers, watching them emerge from the furnaces of supernovae, drift across light years in a silence we cannot hear, dance with our magnetic shield in a ballet older than humanity, paint auroras across polar skies, birth cascades of secondary particles in showers we have only ever glimpsed through instruments and calculation. We have traced their paths through cloud chambers and across the Argentine plains. We have marveled at their energy, puzzled over their origin, wondered at their role in the shaping of life itself, and yet, for all our knowing, they remain what they have always been, travelers in the night, moving without announcement. There is something profoundly soothing in this recognition. In a universe so vast that distance defeats imagination, in a cosmos so old that time becomes almost meaningless, there exists this one steady thing, not loud, not demanding, not dramatic, just a constant, measured, gentle rain of particles that predates your birth and will continue long after you drift into sleep tonight. You are never truly alone beneath the stars, because the stars themselves are always sending their remembrance downward, always speaking to you in the only language they have ever known. The sun breathes its solar cycles, the magnetosphere hums its protective song, the auroras dance when they will, supernovae still explode in distant galaxies, beginning the long acceleration of new cosmic rays that will someday, millions of years hence, pass through worlds and creatures yet to be born. The universe does not rush, it does not hurry, it simply continues its work, moment by moment, in a rhythm as old as the first light that ever traveled through the void. And you, in this moment, in this place, are held within all of it, protected by layers of atmosphere and magnetism, yet always touched by the cosmic rain. The knowledge of this, that you are part of a conversation between the stars and the earth, a recipient of particles born in the violence of stellar death, a witness to physics that unfolds on scales both infinitesimally small and unimaginably vast, this knowledge can rest beside you now, not as urgency, not as wonder that demands action, but as a quiet companionship, a reminder that the universe is speaking to you always, in every breath you take, in every moment of stillness. The cosmic rays continue their fall. They will fall through your sleep tonight, as they have through countless nights before. And perhaps, in that constancy, there is a comfort. In that ancient persistence, there is a lullaby. The universe has been singing this song for 13 billion years, and it will sing it still, whether we listen or not, whether we understand it fully, or remain always reaching toward comprehension. That very reaching, that eternal human curiosity about the cosmos, and its hidden reign, might itself be one of the most beautiful things that the cosmic rays have ever touched as they passed through the world. Rest now in that gentle knowing. The particles continue their slow descent, the stars remain in their places, the magnetosphere keeps its quiet watch, and you, beneath it all, are held in a universe that has been caring for you all along.